So we're going to finish up our coverage of concurrency by giving a quick synopsis of the history of concurrency support in Java. Not surprising because we're doing Java. And you may already know some of this history, but it's worth being aware of it just to be more comprehensive in your knowledge of all things related to Java. So when Java first came out, that was in the middle 90s, version 1.0, and that had support for threads, which of course is the focus of your first programming assignment, and it also had support for so-called built-in monitor objects. And we'll be talking about built-in monitor objects later in the course. And those are both capabilities that exist in the Java execution environment itself. For example, the Java virtual machine, or in the case of Android, the Android runtime, ART, and so on and so forth. And you can learn more about the history of all this stuff at the link at the bottom of the slide. The focus in the first version of Java was on very basic multi-threading and synchronization primitives. So these are kind of just the bare bones you've got to have in order to do concurrent programming. Here's an example of such a thing. This is a program you can get here at this link in my GitHub repository, and it allows multiple threads to communicate and interact by a bounded buffer. A bounded buffer is just a message queue where you can add things to the head of the queue or add things to the end of the queue and then take things off the head of the queue. And that is protected by synchronizers so that there won't be corruption if threads are simultaneously trying to add and remove items from the queue. So we created this thing called a SimpleBlocking BoundedQueue. And then we went ahead and we make a pair of threads. So the first thread here is going to be running so-called producer, which will generate events and stick it onto the queue. And the second thread is a so-called consumer, and that will pull things off of the queue and do something with them. And if you run that little program, you can see exactly what it does. So we have these two threads, we put them into an array. Then we go ahead and start the threads. This is using a good old Java for each loop, which is so like, 2004, but there are better ways to do it now. But this is a nice portable way to do things that'll work with pretty much most versions of Java. And as you can see here, we go through the loop, starting each of the threads. They'll then run, and while those threads are running in the background, the main thread will go ahead and once again iterate through the threads, and it'll join each one. And join is this so-called barrier synchronizer that waits for the thread to finish. And so when all the threads have finished running, when both threads have finished running, then this main thread will go ahead and return and do whatever comes next. So that's very, very simple, basic synchronization. Sorry, basic threading. And a little bit of synchronization, because join is an example of a barrier synchronizer. If we look over here, you can see a little snippet of one of the methods in the SimpleBlocking BoundedQueue, which is the take method. The take method is intended to allow one or more threads to get an item from the queue, blocking if the queue is empty. And so as you can see in this particular case, we use something called the intrinsic lock, which is the this parameter, and we go ahead and we synchronize on it. Synchronized is a keyword that says, wait until there's no other threads in this critical section, and then let one thread in. So if there's a thread that's currently running in here that has the lock, other threads that are trying to get in have to wait. Think of it like the analogy I always love to use is a restroom on an airplane where you have two states, occupied and vacant, and the rule is there's one person allowed at a time. Of course, you can't wait at the front of the plane, but if you go to the back of the plane, you can wait at the back of the plane in line, and when somebody leaves, you can go in. So it's basically one person in the critical section at a time, and you queue up waiting to get your chance to go. So that's basically what this is. It's a synchronized statement. And then, as you can see, if the queue is empty or while the queue is empty, we're going to wait because there's no sense in spinning, trying to acquire something from an empty queue. We want to basically park ourselves and go to sleep, waiting for someone to put an item into the queue. And when someone puts an item into the queue, then that will cause wait to be released. Assuming at some point the queue is no longer empty, we come in here, we notify all the waiters that we're taking something out of the queue, and then we go ahead and we call poll, which removes the first item. And on the way out of this synchronized statement, then the lock is released, the intrinsic lock is released, allowing somebody else to come back in. Very, very, very simple form of synchronization. Very efficient, but very, very simple. So from an analysis point of view or an evaluation point of view, the mechanisms that are provided in the first version of Java for concurrency are very efficient. They're typically implemented either at the hardware level or very thin layer on top of the operating system threads. However, they're also rather low level and limited in what they can do. As a consequence, there's a lot of so-called accidental complexities. Accidental complexities are problems or challenges that arise from limitations with software techniques, software tools, software methods. So using low-level APIs is an example of an accidental complexity. And as we will see, of course, there's many better ways to do this later, which we will cover. With Java, in the context of Java 5, which came out in 2004, they added a bunch of new features that related to concurrency. So they added something called the Executor Framework, which we'll talk a lot about later, a whole gaggle of synchronizers, some things called blocking queues, atomic operations, and concurrent collections. And we're going to cover all of these things in this course. This is really actually kind of a nice summary of most of what we cover in this course. So all that stuff from Java 5, plus a few other things that came a little bit later. As you can see, that what was here was actually not in the Java execution environment layer, which is what the threads and built-in monitor objects were. It's in something called threading and synchronization packages. So these are essentially standard libraries called the Java class library that are part of the Java platform. The focus in Java 5 or JDK 5, or JDK 1.5, they have different names for this stuff, but it's basically 5 something or other, was a focus on so-called coarse-grained task parallelism. And the basic idea, as you can see here, is you create something called a task. We'll talk more about what a task is in a moment. And you submit the task, and the task then is put onto a queue, and then there's a pool of threads, typically one or more, usually as many threads as there are cores on your CPU, typically. And what will happen in this particular case is that when one thread in the thread pool is available, it's not doing anything else, it'll go and pull an item off the work queue, and then it'll go ahead and perform the operation, and then when it's done, it'll put it back someplace else. There's a whole bunch of different models here. This is what's called the Executor Completion Service. And when things are finished, they get into something called a completion queue, and then clients can come and take the results that have been run and completed asynchronously by a thread in the pool of threads. So it's coarse-grained task parallelism. And what that means is that multiple tasks can run concurrently. And back in the day, back in the 2004-ish timeframe when this was first released, there weren't very many cores on multi-core processors. 2 cores was pretty typical. If you had 2 cores in 2004, you were doing pretty well. If you were really cool, you had 4 cores. So that was like a big deal. But the point was there weren't a lot of cores. So things were focusing on so-called coarse-grained task parallelism. We'll talk later about fine-grained task parallelism. Here's an example. This is a fun example, actually not unlike your implementation that you're doing, although this is much more stripped down and simple than what you do. This is a program you can find in my GitHub repository called the Palantiri Manager application. And what it does is it creates a fixed size thread pool and coordinates the starting and stopping of multiple tasks that acquire and release shared resources. So you can see here we use the new fixed thread pool factory method on the executor's utility class. We'll talk more about what that stuff is later. And that's going to go ahead and create a pool of threads that is equivalent to the number of beings that want to gaze. And they're going to work off of what's called a shared unbounded queue. We'll talk about that later too. Then we go ahead and we create a couple of barrier synchronizers. The idea of this is we start all the threads up in the pool, but we want them to hold their horses, think like a horse race, at some starting point so that they don't begin to run until they're all ready to run. We don't want one to get an advantage just because it showed up first. It was created first. Think again about a horse race, or better yet, see, the Olympics are coming up. They will not be doing a lot of track and field in the Winter Olympics. But if it was the Summer Olympics, they would be doing track and field. And you have everybody start at the starting gate. It wouldn't be fair if you had one of the athletes who ever got to the starting gate first just started running, right? That wouldn't be fair. They'd win the race probably because they'd get a head start. So a cyclic barrier allows what's called an entry barrier, which says everybody has to wait till they're all ready to go, and then they can all start off in unison. So that's what a cyclic barrier does. We also have this thing called a countdown latch, which is used actually as a so-called exit barrier that says when everybody's finished, or as each being finishes doing its thing, it'll decrement this count atomically. And then you know when you're finished. And then the last thing we do here is for all the beings, we're going to go ahead and say execute a runnable that we make with the number and the entry and exit barrier. So we'll cover that stuff in more detail. You will learn a lot about this with one of the assignments. I can't remember whether it's assignment 3 or 4, but you'll get a chance to see how to program these APIs. So the good thing about Java 5 was a very feature-rich, very optimized, lots of cool stuff. We will cover all these synchronizers and thread pools and so on in great detail later. However, it was also somewhat tedious and error-prone to program. You had to be responsible for a lot of low-level details. And the other problem that it had was that coarse-grained task parallelism doesn't really scale very well for modern multi-core processors. So what we'd like to have is we would like to have the performance keep going up and up and up. As we get more processors, we'd like to have basically almost this sort of linear improvement in performance. But what was happening was that we weren't getting quite the performance that we expected. And one reason for that was the programming models weren't well suited to maximizing concurrent and parallel processing. Now, we're not going to spend a whole lot of time in this class talking about ways to address that. That's actually my companion class that I teach in the fall, which is CS 253, which focuses on parallel functional programming. So for now, we won't worry about this too much, but that's what is the way that things were done then. And because of this, because of the scalability issues, that's what motivates these other parallel programming frameworks. So things like completable futures, things like parallel streams, things like reactive streams, all of which are things I'll cover in my other class. So that's the end of the history of concurrency support in Java. So we're going to focus in this class primarily on the stuff in Java 1. That's really what your first programming assignment is about, threads. But that's, as you'll see, a little bit too simple and has some tedious and error-prone issues. So we're going to focus primarily on the Java 5 stuff and some Java 7 stuff that we'll also talk about later. Okay, so that's a quick overview.